Right now, the James Webb Space Telescope is doing something no instrument has ever managed to do before. It is looking directly at Pluto, separating its faint heat signature from the glare of its enormous companion moon Saturn, and reading chemistry off a surface 4 billion miles away with a precision that simply did not exist 5 years ago. And what it has found in the last several months is forcing planetary scientists to rewrite their understanding of a world most people stopped thinking about the moment it lost its planet status back in 2006. Pluto is not the dead, frozen, forgotten leftover everyone quietly assumed it still was. It is actively refrigerating its own atmosphere using nothing but suspended haze particles. It is hiding a chemical signature on its surface that matches no known substance in the entire scientific literature. And it may be sitting on top of a liquid ocean, kept warm not by a nearby planet's gravity, but by something happening deep inside its own core. Today, we are going to walk through exactly what Webb saw, why it took this long to finally see it clearly, and why the answers are raising even more questions than anyone had expected. To understand why this moment matters so much, you have to go back to where Pluto's story actually began. In 1930, a 24-year-old research assistant named Clyde Tombaugh was working at an observatory outside Flagstaff, Arizona. His entire job was to compare photographic plates of the same patch of night sky taken days apart, searching for a single point of light that had shifted position against the fixed backdrop of stars. After months of painstaking comparison, he found it. A dim, moving dot that became the 9th planet in our solar system, a designation it would hold for the next 76 years. For most of the 20th century, Pluto remained little more than that same dim dot, too small and too distant for any Earth-based telescope to resolve into anything resembling a real surface. The first genuine look came decades later, and it came at enormous cost. In July 2015, NASA's New Horizons spacecraft completed a 9.5-year journey across nearly 3 billion miles of space and screamed past Pluto at more than 30,000 miles per hour. There was no orbit. There was no second chance. The spacecraft had a single narrow window of close approach before it continued on into the darkness of the Kuiper Belt, never to return. What it captured in those few critical hours rewrote almost everything scientists thought they understood about this small, frozen world. A vast, pale, heart-shaped plain of nitrogen ice stretched across a significant portion of the visible surface, smooth and strangely young-looking in a way that hinted at ongoing geological activity. Mountains built from solid water ice rose more than 10,000 feet into the thin sky. They're frozen so hard at Pluto's temperatures that they behave structurally more like granite than anything most people picture when they hear the word ice. Layers of blue haze rose hundreds of miles above the surface, visible only when backlit by the distant sun, structured in ways that told researchers something dynamic was happening in that impossibly thin atmosphere. New Horizons answered decades of open questions in a matter of hours, and it opened roughly twice as many new ones in the process, but it only had that single flyby. Anything it missed would stay missed unless a different kind of instrument eventually came along to pick up where it left off. That instrument turned out to be the James Webb Space Telescope, though not in the way most people expect when they picture it. Webb is not primarily a camera in the conventional sense. Its real power lies in spectroscopy, the process of breaking incoming light apart into its individual wavelengths with extraordinary precision in order to read the chemical fingerprint of whatever it happens to be observing. Every molecule absorbs and emits light at specific, unique wavelengths, and if you can measure those wavelengths precisely enough, you get a full chemical inventory of a distant world without ever sending a spacecraft anywhere near it. Pointed at a faint pinprick of reflected sunlight 4 billion miles away, Webb can determine which molecules are present on a surface, how warm different atmospheric layers actually are, and how those conditions shift over time. The specific technical barrier Webb had to break through with Pluto is one that frustrated researchers for years. Pluto and its enormous moon currents sit so close together in Earth's sky that older telescopes simply could not separate their individual thermal signals. Any attempt to measure Pluto's own heat emission would inevitably pick up contamination from Charon sitting right beside it in the field of view, blurring the results past the point of usefulness. Webb's much larger mirror, combined with its far more sensitive mid-infrared instrument known as MIRI, which operates across wavelengths from roughly 5 to 27 micrometers, finally solved that problem. For the very first time in the history of Pluto science, researchers could read Pluto's own thermal emission cleanly separated from its companion, producing an atmospheric diagnosis that had simply been out of reach before now. A team led by astronomer Tanguy Bertrand at the Paris Observatory used data Webb collected across 2022 and 2023 to confirm something that had sounded to many of their colleagues almost too strange to be real. Their findings were published in the journal Nature Astronomy in June 2025, and they confirmed a prediction first made 8 years earlier, in 2017, by planetary scientist Xi Jiang at the University of California, Santa Cruz. Zhang's original hypothesis had struck enough of his peers as unlikely that he later described it himself as a crazy idea. His proposal was that the haze particles suspended in Pluto's atmosphere were not trapping heat, the way similar haze traps heat on Saturn's moon Titan. Instead, he argued, they were doing the exact opposite. They were absorbing sunlight during Pluto's brief day and then radiating that energy straight back out into space as infrared heat faster than Pluto's extremely thin atmosphere could ever hold on to it. Not a blanket, a radiator, actively pulling heat away from a world that barely had any warmth to spare in the first place. Webb's mid-infrared data confirmed this directly. The haze particles in Pluto's upper atmosphere are genuinely controlling the entire planet's energy balance, heating and cooling in a continuous cycle as they absorb and then release radiation. The net result is that Pluto's upper atmosphere is running roughly 30 degrees Fahrenheit colder than existing climate models had predicted it should be. Bertrand described this to live science as a genuinely new kind of climate, unlike any other atmosphere found anywhere else in the solar system. On every other world, scientists have studied in detail. The gases themselves do most of the work of regulating atmospheric temperature. On Pluto, it is the solid particles suspended inside those gases that are running the entire show. Researchers now believe similar haze-driven cooling might be happening on other distant hazy worlds, including Neptune's large moon Triton, and possibly happened in Earth's own atmosphere billions of years ago, long before oxygen built up in our skies and fundamentally changed the underlying chemistry. That connection to early Earth is worth sitting with for a moment. Pluto's atmosphere today is composed mostly of nitrogen, with methane, carbon monoxide, and small traces of other compounds mixed in. The composition is broadly similar to what many researchers believe Earth's atmosphere looked like in its earliest period, long before photosynthetic life transformed our planet into the oxygen-rich world we know today. Sunlight striking those early Earth molecules would have driven many of the same photochemical reactions that sunlight striking Pluto's atmosphere drives right now, producing organic compounds, building haze, and slowly distributing new chemistry across the surface below. Pluto, sitting in permanent deep freeze at temperatures where chemistry moves painfully slowly but never fully stops, has been running a version of that ancient pre-life atmospheric chemistry continuously for roughly 4 billion years. That makes it far more than a frozen curiosity at the edge of the solar system. It is a working, real-time model of conditions that once existed on Earth but disappeared here long ago, preserved only because Pluto is cold enough to hit pause on a process the rest of the solar system moved past billions of years ago. That same photochemistry is directly responsible for one of Pluto's most visually striking features, a dark, reddish-brown material that colors large portions of the surface, concentrated especially in a broad equatorial region roughly the size of Alaska. These compounds, known as tholins, form when sunlight breaks apart methane and nitrogen molecules high in the atmosphere. The resulting fragments recombine into heavier, darker organic compounds that slowly drift downward and settle onto the surface over immense stretches of time. Tholins belong to the same broad chemical family as some of the organic molecules researchers believe may have played a role in the chemistry that eventually led to life on early Earth. On Pluto, that same slow production of biological building blocks has been running uninterrupted for billions of years, quietly settling onto a surface too cold for any of it to ever go anywhere or react further. A 4 billion year snowfall of organic chemistry landing endlessly on a world where surface temperatures sit nearly 400 degrees Fahrenheit below zero, and nothing is ever warm enough to do anything more with it. Those temperatures deserve a moment of their own. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth. Surface temperatures there sit somewhere between roughly negative 387 and negative 369 degrees Fahrenheit. At those levels, nitrogen, the same gas that makes up about 78% of the air currently filling your lungs, freezes completely solid and becomes part of the physical landscape. Atmospheric pressure at Pluto's surface measures around 13 microbars, compared to Earth's roughly 1 million microbars. Even inside a fully protective suit, cold at those extremes would begin damaging exposed equipment almost instantly, long before the near total absence of breathable air ever became the more immediate danger. Now, for the discovery that is so new, researchers are still actively working out what it even means. In June 2026, a team led by Bruno Bazar at the Paris Observatory submitted a paper to the journal Astronomy and Astrophysics, describing a detection they framed in unusually direct terms for a scientific publication. While analyzing Webb infrared data collected from both Titan and Pluto in a narrow wavelength range, centered near 5.11 micrometers, a spectral window where haze absorption happens to be low enough for the instrument to actually see through to the surface below. The researchers found an absorption feature they simply could not identify, a specific dip in the spectrum marking a wavelength where light was clearly being absorbed by something, with no obvious candidate for what that something might be. They checked the entire published planetary spectral literature. They found no documented molecule, no known gas, and no confirmed ice compound from any prior study of any solar system body, or any exoplanet ever observed, that produces an absorption signal at that exact wavelength. The feature showed up twice in the Titan data, captured by two separate Webb instruments operating across two different wavelength ranges, collected months apart from each other. That detail matters enormously, because a signal appearing in only one instrument at one single moment could reasonably be dismissed as a glitch or an instrumental artifact. The same signal showing up independently in two separate instruments is far harder to wave away. And then the exact same feature appeared again in Pluto data collected back in May 2023 at essentially the same wavelength, well within the telescope's margin of measurement error. Two entirely different worlds, sharing an unexplained absorption signal at a wavelength that matches nothing currently in the scientific record. Titan and Pluto could hardly be more different from each other on paper. Titan sits roughly 4 times closer to the Sun than Pluto, is significantly larger, and has actual liquid methane lakes and rivers flowing across its surface. Pluto, by contrast, is frozen completely solid, much smaller, and orbits far out in the depths of the Kuiper Belt. What the two worlds do share is atmospheres dominated by nitrogen and methane, and surface chemistry that has been slowly evolving for billions of years in environments completely lacking free oxygen. The research team proposed several candidate compounds that could theoretically produce a signal near that wavelength, including certain configurations of complex hydrocarbon molecules, possibly benzene, mixed with an as-yet unidentified partner compound, or forms of acetylene or ethane ice. None of these candidates has been confirmed. The authors were explicit in stating plainly that they cannot yet say what the molecule actually is. The Dragonfly mission, a rotorcraft lander currently scheduled to reach Titan in the early 2030s, carries instruments that could eventually help narrow down the possibilities by analyzing Titan's surface materials directly on site. But that mission remains years away, and even once it arrives, it will not be able to observe this specific spectral feature directly in the way Webb has. For now, the unknown molecule stays exactly that. Unknown. Present on two very different worlds, matching nothing in the existing database and waiting for an explanation that may not come for years. Before we go further into what else Webb has uncovered, it's worth pointing out that keeping up with discoveries moving this fast is exactly the kind of thing this channel's sponsor makes easier. If you're the kind of person who wants to actually understand the science behind headlines like this one instead of just skimming a summary, today's sponsor offers courses built specifically around space science and astrophysics, taught by working researchers rather than generic narrators. Check the link in the description for a discount on your first month, and you'll be reading Webb data almost as fast as the researchers publishing it. The story of everything Webb has revealed about Pluto across 2025 and 2026 is really a story about what a single, sufficiently sensitive instrument can do once it finally has the resolution to separate signals that were previously too faint or too tangled to read cleanly. Take the staining pattern on Charon's poles. Pluto is steadily losing roughly 1.3 kilograms of methane per second to space, with about 2.5% of that escaping material eventually captured by Charon's gravity and freeze-trapped onto its polar regions, where solar radiation slowly converts it into permanent dark organic compounds. Researchers had suspected this mechanism for years, but they could not confirm it in the level of detail Webb now provides. The carbon dioxide and hydrogen peroxide frozen onto Charon's surface, confirmed by Webb data back in 2024, had never actually been detected there before that observation. The mystery absorption feature on both Pluto and Titan was only visible inside a narrow wavelength window that earlier instruments simply lacked the sensitivity to probe at all. Pluto, it turns out, has been hiding almost all of its real complexity from every single instrument that came before the one now reading it clearly for the first time. To fully appreciate what Webb is adding to the picture, it also helps to spend a little more time with what New Horizons revealed back in 2015 and what continued analysis of that same dataset has kept turning up in the years since, because the surface of Pluto is strange in ways that extend well beyond its atmosphere alone. That heart-shaped plane that became the single most iconic image from the New Horizons flyby is formally named Tombaugh Regio, after Clyde Tombaugh, the young astronomer whose careful comparison of photographic plates first revealed this world's existence. The pale western lobe of that heart-shaped feature is a basin of nitrogen ice named Sputnik Planitia, roughly the size of Texas, filled with ice that is visibly churning in slow convective cycles. In convection, warmer material rises, while cooler material sinks in a continuous, ongoing pattern of circulation. On Earth, you see the same basic process in a pot of boiling water, or in the gradual movement of tectonic plates deep below the surface. On Pluto, the heat driving this convection appears to come from the slow radioactive decay of elements buried inside its rocky core, deep beneath the visible ice. The surface ice above that core moves in enormous polygonal cells, each one hundreds of miles across, turning over completely on timescales, stretching hundreds of thousands of years. A world that was supposed to be entirely dead, with no internal heat and no ongoing geological activity, just a frozen remnant sitting passively at the edge of the solar system is in fact still moving. The inside of Pluto has not finished cooling down. That lingering internal warmth leads directly into one of the most debated hypotheses surrounding Pluto today. Multiple independent lines of evidence point toward the possibility of a liquid water ocean buried somewhere around 100 miles beneath the frozen surface, kept from freezing solid by that same slow radioactive heat driving the convection visible in the nitrogen ice above it. The evidence for this is not a single direct detection. It is a consistent pattern spread across several separate observations. The cracks and ridges crossing Pluto's surface line up in ways that closely match what researchers would expect from a subsurface liquid layer shifting and flexing gradually beneath a solid crust. Sputnik Planitia sits directly above what appears to be a positive gravity anomaly, a location where the underlying mass distribution is measurably denser than the surrounding ice. On a tidally locked world like Pluto, heavier surface features naturally rotate over time to face the largest nearby source of gravitational pull. Sputnik Planitia faces directly toward Charon, exactly where you would expect it to end up if something dense and liquid sat beneath it, gradually causing that section of the crust to reorient itself across enormous stretches of geological time. Then there are the cryovolcanic mountains discovered near Pluto's south pole, two enormous isolated peaks rising somewhere between 13,000 and possibly 20,000 feet above the surrounding terrain, with deep depressions at their summits and flank features that closely resemble cooled flows of material. Add that piece to the puzzle, and if these really are genuine cryovolcanoes, which the geological evidence strongly suggests, then at some point in Pluto's history a thick slurry of water, ammonia, and other compounds was forced upward from a deep liquid reservoir all the way to the surface. Something warm enough to remain liquid existed inside this frozen world, and quite possibly still does today. This possibility matters enormously for how scientists think about liquid water across the outer solar system more broadly. Hidden oceans are already confirmed or strongly suspected beneath the icy surfaces of Jupiter's moon Europa and Saturn's moon Enceladus, both of which show far more dramatic surface evidence of what's happening underneath them. Enceladus actively erupts geysers of water vapor into space through cracks near its south pole. Europa's surface features closely resemble the broken pack ice found in Earth's Arctic regions, strongly implying ongoing movement of liquid water somewhere beneath its shell. But both of those moons sit much closer to large planets whose gravitational tidal forces generate the heat that keeps their interiors liquid in the first place. Pluto has no large neighboring planet to squeeze it that way. If Pluto really is hiding an ocean, it is being kept liquid by radioactive decay alone, which would mean internal heat from radioactivity, a process running to some degree inside nearly every rocky body in the solar system. Is sufficient by itself to maintain liquid water even on a small, frozen world sitting billions of miles from the sun. If that turns out to be true, it fundamentally changes the calculation for how many places in the solar system might realistically host liquid water, pushing that number dramatically upward. Every large icy object out in the Kuiper Belt suddenly becomes a genuine candidate, and there are hundreds of thousands of those objects still waiting to be studied. There's one more piece of terrain worth walking through before we zoom back out, because it adds yet another layer of strangeness to Pluto's already crowded surface inventory. A region called Tartarus Dorsa, photographed by New Horizons during the 2015 flyby, is covered in tall rows of jagged blades made from frozen methane, arranged in long parallel ridges, some rising more than 1,500 feet into the thin sky. Nothing resembling these formations had ever been photographed anywhere else in the solar system before that moment. Researchers believe they form through a process similar to penitentes, ice formations found in high-altitude deserts here on Earth, where they typically grow no taller than a few feet. Uneven sunlight causes sections of icy surface to sublimate at different rates, carving taller sections while lower areas erode away faster, gradually sculpting narrow, blade-like ridges over time. On Pluto, that same basic process plays out on an enormous scale, using methane ice instead of water ice, under temperatures and pressures nothing like anything found on Earth. A 2025 reanalysis of the original New Horizons dataset suggested these blade fields may wrap around as much as 60% of Pluto's equatorial belt, forming an almost complete ring of jagged, frozen terrain circling the entire dwarf planet. Researchers studying the New Horizons dataset have pointed out that Tartarus Dorsa's blade fields also complicate any future landing attempt, since a lander descending into that terrain would be setting down among ice formations, sharp enough to shred a spacecraft's landing gear on contact. That detail alone reshapes how mission planners think about where a hypothetical future Pluto lander could safely touch down. Assuming a mission like that ever gets funded in the first place, It's a small reminder that every new discovery about Pluto isn't just scientifically interesting. It also directly changes the practical calculus of how humanity might eventually explore the place in person. Put all of these pieces together, and the picture that emerges is almost the exact opposite of what everyone assumed about Pluto before 2015. Not a dead, passive, frozen lump sitting quietly at the edge of the solar system. A world with genuinely active surface geology. An atmospheric cooling mechanism confirmed by Webb in 2025 that has no known parallel anywhere else. A slow chemical machine that has spent 4 billion years producing organic compounds belonging to the same family as molecules relevant to the origin of life. An ongoing atmospheric exchange with a companion moon that has been permanently staining Corin's poles for billions of years. An unidentified molecule sitting right on its surface that also appears on Titan and matches nothing currently in the scientific literature as of 2026. And strong geological evidence pointing toward a hidden liquid ocean that would make Pluto one of the most potentially significant worlds in the entire outer solar system. None of this has changed Pluto's formal classification. It remains, under the International Astronomical Union's current definitions, a dwarf planet, and the periodic debate over whether that definition should be revisited, which occasionally resurfaces whenever a NASA administrator or a prominent scientist raises the question publicly, is really a separate conversation from the science itself. What the science has actually done is make that label feel increasingly inadequate as a description of what Pluto really is. The classification says small, cold, distant, unimportant. The data, collected piece by piece across a decade of analysis and capped off by everything Webb has confirmed over the past 2 years, says something else entirely. Active, complex, chemically rich, geologically alive, and still, right now in 2026, generating discoveries that nobody saw coming. Webb is scheduled to keep observing Pluto periodically as the world cycles back into optimal viewing position within its orbit. Each new observation adds fresh data points to an already growing picture. The thermal light curves researchers use to track how Pluto's heat emission changes as the planet rotates are sensitive enough to reveal variations between different terrain types, letting scientists build an increasingly detailed model of how heat actually moves across the surface and up into the atmosphere over the course of a full rotation. The mystery absorption signal near 5.11 micrometers will remain a priority target for follow-up investigation, both through additional Webb observations and through laboratory chemistry experiments aimed at synthesizing candidate compounds, and testing whether any of them can reproduce a matching spectral signature under Pluto-like conditions. The cryovolcanic mountains will continue to be cross-referenced against the ever-expanding archive of New Horizons data, a dataset scientists are still actively working through more than a decade after the spacecraft transmitted its full haul of information back to Earth. There is currently no funded mission in development to send a dedicated orbiter or lander back to Pluto, largely because the travel time alone, even accounting for gravitational assist maneuvers, runs to a decade or more, and space agencies have to weigh that enormous timeline against faster missions closer to home. The most recent Planetary Science Decadal Survey, which sets NASA's exploration priorities for the years ahead, identified a Uranus orbiter and probe as the top recommended flagship mission for the coming decade, with the ice giants generally considered a higher near-term scientific priority than the Kuiper Belt. That could change as the growing complexity of Pluto and similar Kuiper Belt objects becomes harder to ignore. But for now, that remains the current reality. Webb is the only instrument reading Pluto in this level of detail, and it is likely to remain the only one for the foreseeable future, which makes every new observation it returns from that direction matter more than it otherwise would if a dedicated mission were already on its way. A world that was formally voted out of the planet category in 2006, a world that sat largely unexplored for 85 years after its discovery, a world that was expected to be geologically dead and atmospherically trivial, a world everyone assumed was hiding nothing worth looking for because there was supposedly nothing left to find. It turns out Pluto has been hiding almost everything. A world that was dismissed, formally demoted, and then, largely forgotten by the public, is now revealing, instrument by instrument and observation by observation, that it has been quietly doing things no other world in the solar system does, including some things science does not yet have the vocabulary to fully describe. Webb is still watching, the data keeps arriving, and somewhere out past Neptune, a small frozen world that most people wrote off 20 years ago is turning out to be one of the strangest places we've ever looked. Subscribe now if you want to be here for whatever this small, frozen, endlessly surprising world reveals next.